This recording is for Primary Math 4, working in the intensive practice book at the word problems between pages 12 and 17. Number 1, we're trying to solve some riddles. The first one tells us that it's a number between 20 and 30, a multiple of 4 and 7. So to find this number, we're going to start with the multiples of 4 between 20 and 30. When it says the word between, by the way, it means not including either 20 or 30, but the numbers between them. So the multiples of 4 that are between 20 and 30 are only 24 and 28, and 28 is the one that is also a multiple of 7. 21 and 28 would be the options for multiples of 7. So 28 is the one that meets both criteria. Part B, a number between 30 and 40 that is a factor of 70. And maybe you see that right off and realize that 2 times 35 is equal to 70. So the number that we have that we're looking for is 35. You might need to do a factoring list. 1 times 70, 2 times 35, and of course there you found it. But you could continue and find the other factors of 70. And sure enough, 35 is the only one that meets the criteria of being between 30 and 40. Part C, I'm an odd number, smaller than 50 but greater than 30. So again, between 30 and 50, it's an odd number. It's a multiple of 7 but not of 5. So let's think about the multiples of 7 between 30 and 40. That would start with 35, 42, and 49. If it's an odd number, then it's not 42. It's a multiple of 7 but not of 5. So 35 is out. The answer we're looking for is the number 49. Part D. I'm a number greater than 10 but smaller than 40. So those are my boundaries. A factor of 56 but not a multiple of 4. So let's think about the factors of 56. 1 times 56, then try the 2's. 2 times 28. Now 28 is in the right age or in the right range. It's between 10 and 40, but 28 is a multiple of 4. So that one doesn't work after all. The next one I can do is 4 times 14, and 14 does actually work. It's between 10 and 40. It is not a multiple of 4. The last set of factors of 56 are 7 times 8, and of course that one is not in the right number range. So we've solved the riddles, not overly hard, just help us get to thinking about numbers with these kind of criteria. Number 2, we start out with water in a bucket, we use some, and we're trying to find out how much water is left in the bucket. Depending on your student, you might want to draw something that's a little bit concrete for them. And if you have 6,500 milliliters in the bucket and you use 3 liters and 25 milliliters of it, so here's the water that we use up, and when we're finished, our water line is down to here, and the part in there that we used is 3 liters, 25 milliliters. And of course the 6,500 is given to us as milliliters. Great time to make sure that everybody is thinking about units. 3 liters, 25 milliliters can be written as 3,025 milliliters. Don't forget about the 0 for the hundreds place, because liters are thousands of milliliters, right? And so how much water is left in the bucket, we're going to subtract the two numbers. It's basically, at its core, just a subtraction problem. You do have to convert liters and milliliters into milliliters. Use your mental math muscles. If I have 6,000, take away 3,000, then I have 3,000 left. If I have 500 and I'm taking away 25, I'll have 475 left. And The question is, how many milliliters will I have left in the bucket? And so the answer is 3,475. Watch the units, watch how the question is asked, make sure you answer exactly what is asked. Number 3, Mr. Trucker drove 392 miles to Looneytown on Friday, and then Saturday he drove 59 miles further than on Friday. So if on Friday, here's our Friday drive, he drove 392 miles. On Saturday, he drove 59 miles further than he did on Friday. So here's our 392 portion, but then he drove another 59 miles. And this was the portion of the drive that he did on Saturday. The question is, what was the total distance he traveled on the 2 days to the nearest 100 mile? So we're going to round to the nearest 100, but we're not going to round until we're finished. Okay, so let's pick this up with this. In the hundreds, we have 600s. Again, we want to stretch mental muscles anytime we can. So I have 600s, but in my tens place, I have another 100, right? And so that'll be 700s. When I use one of the hundreds, actually, look what's going to happen. I'm going to have 200s in there. So let me change that. We'll make it a 900. Having trouble addition here. Let me try this again. I have 600s in the hundreds place. In the tens place, I'm going to have 2 more hundreds. 6 and 2 is 8 hundreds. And to make that 100, I use this 5 and put one of them with that 9 and one of them with that 9. So now I have 3 hundreds left over, but don't forget to consider the ones column. That gives me another 10, because in this case, I'm going to use one of these to make a 10 there. So I had 3 10s here. And I have another 10 carried over. That's 4 10s. And I have 3 left over. 843 miles. If we want to have it to the nearest 100, we're going to round down to 800 miles. You really cannot round until after you're finished. Notice if you rounded before, you'd have 400 and 460. And that would round up to 900. So by adding first and rounding second, we took care of that. It's more accurate. When I do the mental math like this, it is easy to make a mistake. It takes a lot longer to do it in some respects than if I just wrote it down and added right to left. Saying it out loud makes it take longer. Just doing it in my head, I can keep up with things because I've done it for a while. Don't shortchange your children into just doing it the quick, quote-unquote, quick way of right to left. Help them to persevere through left to right so they can learn the skill and become fast at it. I'm sure by now in class I've told you my crawling and walking analogy, and it's very applicable. Okay, then we have a duck. I'm not very good at drawing ducks and chickens, so I'll just use letters. The duck weighs 3 kilograms and 55 grams. A chicken is 415 lighter than the duck. So then how much do the chicken and the duck weigh altogether? A couple of ways you could do this. One method would be to find how much the chicken weighs and then add them together. That's a good way to do it. And one thing I can do with that, if it's 415 lighter, what I probably would do would be to take the 415 out of 1 whole kilogram. And that means I would have 2 kilograms. And I would have 585 grams plus the 55 grams from here. All told, that would give me 2 kilograms and 640 grams for the chicken. So if the duck weighs this and the chicken weighs this, then all together they weigh 5 kilograms and 695 grams. That's their together weight. Now, anytime possible, I love to show a couple of methods just because it's a good thing to be able to do it two different ways. Think about the numbers in different ways. Another option would be to realize if I took the duck, I might even just make them into grams just because it's easier, and I doubled it, and then I subtracted the 415 because it's easy to double something, and subtracting the 415 afterwards is fine and dandy too. So I would have 6,110, take away the 415. Mental math, how do we want to do it? I could take away the 110, that would leave me with 6,000, and I would have 305 left to take away. 6,000 take away 305 is 5,000. Am I going to get myself in trouble here? No, I'm right. There we go. It worked. 5,695, which again is 5 kilograms, 695 grams. Which way is best? Depends. It doesn't matter, of course. Maybe one seems easier to you or to your student, but it's always good to challenge yourself to see one way and then also find another way to do it, because you're demonstrating that you have a good grasp of the question and what it's asking and how to solve it. Number 5, we have 3 pieces of string. They are 64 inches and 80 inches and 96 inches long. And they're going to cut them into shorter pieces of equal length without any wastage or any leftover, and they want to know the longest possible length of each piece. So let's think about this a second. Of course, you could cut them all into 1-inch pieces because you'd have 64 from this string and 80 from the next and 96 from the next. I could cut them all into 2-inch pieces because they're all even numbers. The question is, what is the longest piece of string that I can cut it into without having any waste? I could cut them all into 50-inch pieces, but then there'd be waste, right? This would be a 50, and I just have to throw the 14-inch away because it's not a matching piece. So that's what they're talking about. All of these work, but we want the longest possible. 50 works, except I want no waste. So we have to make sure that it works out evenly. So to do this, basically what we're trying to do is factor. The factors of 60, I always start with 1 and increase from there. 2 times 60, or 2 times 32. 3 doesn't work. Remember the trick? 6 times 4 is 10, and 10 is not a multiple of 3, so I know 3 won't work. If you add the digits and the answer, the sum, is a multiple of 3, then 3 goes into it. How do I know if 4 goes into it? Well, if 2 went into it and left an even number, then I can take another 2 out of it. So if it's 2 times 32, then it's 4 times 16. We want to get as good as possible at all these tricks. 5 doesn't work. I know 6 doesn't work because 2 and 3 would have to work for 6 to be a factor. Since 3 is not a factor, 6 cannot be. 7 doesn't work. 8 times 8 works. And that tells me I'm finished because my 2 numbers have met up. Same thing on the next set of numbers. I want 1 times 80. 2 is going to work. 8 plus 0 is 8, so 3 is not going to work. 4 will work. It'll be 4 times 20. It's a multiple of 5. That'll be 5 times 16. 6 doesn't work. 7 doesn't work. 8 times 10 works. 9 doesn't work, so I'm through with that. And the last set of numbers, 1 times 96, 2 times 48. 3 is going to work because 9 plus 6 is 15, and 15 is a multiple of 3. That's a shortcut. If you don't know that, make sure you learn it, teach it to your children. If you add the digits up and the answer is a multiple of 3, then you can divide 3 out of it. So this is 3 times 32. 4 is going to go into it. If it's 2 times 48, it'd be 4 times 24. 2 and 3 both go in, so I know 6 does. Of course, I know 5 does not. So this will be 6 times 16 and 8 times 12. What we want to do is find the largest common factor, and I'm going to start with these numbers. 96 I could check for 96, but these don't even go that high. I could check for 80, but it didn't go that high. So I'm going to start with the smallest number and check 64. It's not everywhere. 32 occurs in 2 of the places, but not the third one. But finally we realize that 16 occurs in all 3 places. Now as you're going, you might have found that sooner. At some point you can stop at any point, but you need to be able to compare and make sure you found the highest one, the biggest one, to make sure that that works. Let me do an alternative way of this one as well. So let me think. Yeah, just 16 inches is the answer when we give an answer to it. The question is, what is the longest possible length of each equal piece? And that would be 16. Without finding all of the factors like that, let's talk briefly about another way to solve this. We could say that 64 is 8 times 8. You can do any factors that you think of. And 8 is 2 times 4. And then, of course, 4 is 2 times 2. So I've found the prime factorization of 64 to be 2 times 2 times 2 times 2 times 2 times 2. 80 is 8 times 10. And maybe I take the shortcut and say I know that 8 is 2 times 2 times 2, and 10 is 2 times 5. So the prime factorization is 2 times 2 times 2 times 2 times 5. If I factor 96, I could do 2 times 48. 48 is 2 times 24. Generally, if I don't see one that's really obvious, I really do go with 2 until it quits working. And so 96 is 1, 2, 3, 4, 5 2's times 3. So the greatest common factor, let's see, I have 4 2's here. I have more than that in this one, and more than that in this one, but the greatest common factor is the biggest number that is in every one of these. And there are at least 4 2's in every one of them. Some have more, but they all have at least 4 2's. One of them has a 5, but they don't all have 5's. One of them has a 3, but they don't all have 3's. So the greatest common factor, 2 times 2 times 2 times 2, is equal to 16, and that is going to be our answer. So you can find the greatest common factor either the way on the left by finding all of the factors, or by on the right by factoring down to prime numbers and finding what they have in common. What's the most that they have in common? Either way, you get the same answer. Both methods are good to know for various types of problems. Number 6. Winona wants to buy a computer, a monitor, and a printer that cost $2,285. Her father gives her $1,080, and her mother gives her $120 less than her father did. So she needs to have $2,285. What she has is $1,080. And again, I would probably do this just by adding the $1,080 and then subtracting what her mom gave her less than that. So altogether, what she has is $2,160 subtract 120, or $2,040. Now, if I were really flexing my mental muscles, I would take this one, and I would notice the fact that I have 80 and 80, which makes 160. Mentally, I could know that 160, take away 120, leaves me with 40, and so I'm going to have the 2,000, that stays, and 160 minus 120 leaves me with 40, and I get the 2,040 that way. You can make it a two-step problem, add the 2,080s together and then subtract 120, or you can just subtract the 120 from the 160. But the question is, how much more money does she need? So she needs to have, in order to buy the stuff she wants, $2,285. What she currently has is $2,040. So she must need $245 to buy the things that she needs. Number 7 is broken up into an A and a B part. Peter has 5,680 coins and Paul has 1,897. Round the number of coins that they have together to the nearest hundred. Again, they have to tell you, you have to find the number first and then round, not round and then add them together. So if I add these together, looking at my hundreds place, I definitely have a 10 to move to my thousands place. 5 and 1 is 6, and 1 more makes 7. When I use that 10, I have 4 hundreds left over. Then I'm going to consider my tens place, and sure enough, I get another 100 from there, so that's 5 hundreds. But that uses everything in my tens place. My ones place isn't enough to go any further, so I have 7,507 marbles, or coins, sorry. And if I round that off, that would be 7,500 coins to the nearest 100 coins. Part B. If 28 girls have 273 beads each, what is the estimated number that they have in total? All right, this for years and years, as I used Singapore math with my own children, has always frustrated me that there's no way to really know how they want you to round. Do I do this as 30 girls times 270 beads? Or do I do it 30 girls times 300 beads? There's no way to know unless you look in the back of the book. And indeed, what the back of the book tells us is they did the second method of 9,000 beads. I would say, as long as they rounded, this one is rounded with both numbers to the nearest 10. Personally, I think that's a better answer, because on the second choice, you're rounding one number to the nearest 10 and one to the nearest 100. But they didn't consult me on their answer keys, so that's not the one they used. They did it this way and have 9,000 beads. And it certainly is a much easier estimate, so they went that way. I'm all for being easy when it's possible. Number 8, Mrs. Selvin went shopping with $450. That was her starting point. She would like to buy those items. We're supposed to estimate the cost and decide if she has enough money. Again, how do we round it? We don't know. I think a good rule of thumb is if it's a hundreds number, round it to the 100. If it's a tens number, round it to the 10. And that gives us $370. Does she have enough money? Yes, she does. You know what, actually, I think they rounded this one to the 10 as well. I don't know. Again, I find this rather confusing. How would one know? So, as long as your child is rounding appropriately and getting reasonable answers, I think it's all well and good. So this is 200 and 300. There's another 100, makes 410. Either way, she still has enough money. And the question actually does not ask how much she has. It's estimate the cost, and then did she have enough? And so the back of the book just says, yes, she had enough. That's part A. Part B gets a little more specific. She also remembered she wants to buy a birthday gift, and she found a television set for $168. So she had $43 left over after buying those 3 items. So the estimate is how much money she needs to buy the television set. So if she has $43 and she needs $168, then you could estimate that to $40 and $170, and she needs $130. So estimations are imprecise at best. Again, going with a reasonable answer, even if it's not the same thing as the back of the book, is, I think, just fine. Number 9, of the 64,000 people that visited an exhibit, 30,450 were men, 18,131 were women. How many more adults than children visited the exhibit? So if you say that 64,000 visitors were broken up into adults and children, the adults are broken up into men, 30,450, and women, 18,131, for a total of 48,581 adults. How many more adults than children were there? Well, to find that, I next need to figure out the number of children. So 64,000 minus 48,581, I might think, again, lots of ways to do this, right? One thing that would be pretty easy would be to increase both numbers by 419. And that's easy to do because I have an even thousand there. And that allows me to subtract 49,000. So 64,000 subtract 49,000 is the same thing as subtracting 50,000 and putting one back. So if I subtract 50, I'm at 14,000. If I put one back, I'm at 15,000. 15,419 is the number of children. But we're not finished yet. The question is, how many more adults than children are there? So I have one more subtraction problem to do. Now, as I glance at these numbers, it occurs to me that it's not much borrowing to do. I can do this a little easier because these hundreds can be taken out of these hundreds. So the 48,000 minus the 15,000 is going to give me 33,000. And then I want to find the difference between the other two numbers. To do that, I'm going to help myself with the hundreds. I know that I need 81 to get to 500, and then I need another 81 to get to 581. So the first 81 is because 19 plus 81 make 100. That puts me up to 500, and then I have another 81. So 33,162 is the number of children, no, the number more adults than children that we have. So I tried to color code it to make it easy to follow where I got all the numbers. Maybe it made it visually confusing. There are 33,162 more adults than children. Problem number 10. Aisha has $72 and Esther has $56. How much money must Aisha give to Esther so they both have an equal amount of money? A couple of ways you can do this. I think the easiest is to realize that if I find the total amount of money and I divide it by 2, that's how much they will each have in the end, if they're going to end up with an equal amount of money. The total amount of money is 128 divided by 2 is 64. If Aisha is going to end up with 64, she must give away $8. If Esther adds those $8 in, she also will end up with $64. So the question is, how much money must Aisha give away? And she must give away $8. All right, let's think about an alternative way to solve that. You could also say that right now the difference between these two values is $16. And so if I want to split that equally, I can divide that by 2 and have $8. So if Aisha goes down 8, remember we talked about this before, I don't know if you saw that recording or not, but if she goes down 8 and Esther goes up 8, then the $16 difference is minimized. When you find the difference, don't forget to divide it by 2, because again, if one starts at a certain height and the other starts lower, if they're going to meet in the middle, then this one has to go down some amount and this one has to go up the same amount. Okay, they're not throwing them away, they're giving them to each other. So either way, this one's a little quicker as long as you're sure about the numbers involved and what you're doing with them once you get the $16. Number 11 is one you just have to follow the course of the story and go along with it. Carl collected 165 cards. Then he realized he had 21 identical cards and he gave those away. So now Carl has 144 cards. But now Tessa has 48 more cards than Tessa has 48 cards more than Carl. So if Carl has 144 and she has 48 more, then she must have 192. Now again, the word now is very important. He realized he had identical ones and he gave them to Tessa. Now, that's present tense, after gave, past tense. So Tessa now has 192. What's the question we're asking? How many cards did Tessa have at first? Well, before that, she was given 21 cards to get her 192 cards. So before that, she must have had 171 cards at first, and then she added the 21 cards, which put her at 192 cards, which is 48 more than Carl. There's not really a simple math equation you can do. You have to follow the story and know what each number means. Keep it organized. It's probably helpful to have one chart and one little area for Carl and a different area for Tessa to make sure that you've got it separated. And maybe once you get to the 192, you make it a subtraction problem instead of trying to add backwards. Either way, you're going to get to 171. Problem number 12, Davina, Jean, and Nancy have a total savings of $4,800. Davina saves $480 more than Nancy, and Jean saves $330 less than Davina. One of the first things we have to do is figure out who our base is, and in this case our base is Nancy. Now Davina saved $480 more than Nancy. So here's the same amount, and Davina has $480 more than that. Jean saves $330 less than Davina. So in order to make this something I can use, I have to have something the same. So this is my same block, because Davina has the same amount as Nancy, but $480 in addition. So to use Jean, I really need to start with the same block. So this block is the same as Davina and Nancy, but then how will I show that she has $330 less than Davina? I'm going to add this onto it. I'm going to draw a line here, and maybe I need to rewrite this onto the bottom. This block represents 480. This part of my drawing, if Jean is 330 less than Davina, then this part is 330 and the entire block is 480. It's important to have a diagram that you can read and follow along with. Now we want to know how much does Jean save. What I need to do is get to a point where I can know how much these three blocks are. If I add all of the money total, I get $4,800. If I subtract the 480 that is Davina's And then I got to figure out how much is in this orange box. Well, if this is 480 and this part is 330, then that little box is 150. Now, it might take looking at a little bit. It's amazing what you can come up with when you see the picture and understand what it's talking about. If this pink box of 480 is divided into two groups, one part is 330, then the other part is 150. And since Jean has 330 less than Davina, then she still has 150 more than Nancy. So I would have to subtract the 150 also, and then my 4,800 will be down to just the three blue boxes. Now, again, mental math, you can do this several ways. Generally speaking, I subtract as rarely as possible because it's harder to subtract than to add. If I were to combine the 480 and the 150, I would have 630. 4,800 minus 600 is 4,200. Take away 30 and I get 4,170. Am I finished? Absolutely not. 4,170 are the three blue boxes. I still need to divide that by 3. Think of 4,170 as 3,000 and 1,170. 1,170 can be divided down into 900 and 270. Again, I'm just stretching my mental muscles. 3,000 divided by 3 is 1,000. There are 300 threes and 900. There are 9 tens if I take 27 tens and divide it by 3. So that means I have 1,390 in each of the blue boxes. What's the question I'm asking? How much does Jean save? Jean saves 1,390 plus 150. And that total is $1,540 that Jean saved. You can't solve that problem without walking through it and understanding every bit of it and drawing a picture and following it through. There's no quick formula. You have to really get in deep with the problem, understand it, and solve it. Number 13. Mr. Ching wants to give a group of his violin students some reward stickers. If he gives every student 3 stickers, he'll have 75 left over. If he gives every student 6 stickers, he will need 30 more stickers. So we're trying to figure out how many students there are and how many reward stickers he has. This is another one of those problems that is basically an elaborate guess and check. And to do that, we need to find a way to handle the data. So I'm going to look at how many students we have, and then based on the 3 stickers per student, plus the 75 extra ones, and then also is 6 stickers per student minus the 30, because it says he will run out, he'll need 30 more stickers. Let me make this a little clearer. This is 3 stickers per person. Okay. All right, I pause the recording and finish my chart. 3 stickers per person. And if you do 3 stickers per person, you add 75 stickers. If you have 6 stickers per person, you need 30 more. So what I'm trying to find is basically how many stickers do I have? And if my columns end up being the same number, then I'll know I have the right number of stickers. Because I have, well, let's do one and see what we see. My first thought when I saw this was if you give 3 stickers per person and have 75 left over, kind of like we've been talking about with the remainder theorem, we must have more than 100 students. So I try, or more than 75 students. So I tried 100 students. Now, if I have 100 students and I give 3 stickers per person and I have 75 stickers left over, I must have 375 stickers. If I give 3 to each of the 100 people, that's 300, and then I have 75 extras, that'd be 375. If I give 6 stickers per person, then I would give away 600 stickers, but according to the problem, I run out 30 stickers too soon. So 600 minus 30 is 570 stickers. Now I made another column over here with the difference. The difference here is 195 between these two. What I want is for these two numbers to be the same. Clearly they're not the same. The only reason to keep track of the difference is to know if I've gone the right direction or not. So again, my question was, do I have, my assumption in the beginning was that I had more than 75 students. So that, well, what happens if I go to 200 students? Well, 3 stickers apiece is 600, and that would put me at 675, but this would put me at 1,200 minus 30 is 1,170. This is way bigger. This number is smaller and the distance is growing between them, so that tells me I'm going in the wrong direction. Now, if I just sit down, I know the answer, I worked it out, I could come up with, 2 easy things, try one and then find one that works. But I want you to be able to help your student understand, how do you know when you're guessing and checking, who knows, right? So I said, well, then it occurred to me, I don't know that he gave away as many stickers as possible. I just know that he gave 3 per person and he stopped giving stickers. So then I went the other way and said, well, what happens if he has 50 students? If he has 3 stickers per person, that's 150 stickers, and he has 75 left. That means there's 225 stickers. 6 times 50 is 300, minus 70 is 270 stickers. Now my difference is only a difference of 45. That's getting in the right direction. I went from 195 down to 45. All right, the next thing I tried was 30. If I did 30 stickers, 30 times 3 is 90, plus 75 is 165. 30 times 6 is 180, minus 30 is 150. This distance is 15, but look what happened. Now this is smaller, and it used to be that this column was smaller. 225 was not big enough, but now 165 is too big. So what that means is I've gone too far. My difference between the numbers tells me I've gone too far. Somewhere in between here is the right answer. You also might notice that every time I've done this, I've had an even 10, and every time I'm getting a 5 on this number and a 10 on this number. If I want my numbers to be the same, I can't keep using 10s. So I might try a 35. If I try 35, 35 times 3 is 105. 105 and 70 is 180. 35 times 6, take away 30, is, guess what? 180. So I have found the number of students that meets both criteria. If I have 35 students and I have 180 stickers, you will see that both of the criteria that I'm given work. If I gave away 3 stickers per person, then I have 105 stickers used and I have 75 stickers left over. If I give away 6 stickers per person, 6 times 35 is 180 plus 30 is 210, and that means I am 30 stickers short. I lack 30 stickers from having enough. If I have 180 and I need 210, I'm 30 stickers short. So it's not a simple problem. You can't go from A to B without taking a roundabout course. I even want to show you that when you make an assumption, it may be an altogether wrong assumption. And it took me a couple of steps to realize I had a bad assumption. But there is no way that I'm aware of to estimate that 35 is going to be, or where is the answer? Is it in the hundreds or the tens or the single digits? Except for trying a few in an organized way, coming up with a chart, finding a way to solve it. Number 14 is a problem that can make your head spin a little bit. We have 3 boxes, A, B, and C, and there's a whole bunch of words. I wrote on my paper, I numbered the steps. The first step, the first instruction it said was 7 ping pong balls went from A into B. The second step was that 3 ping pong balls went from B into C. The third step was that 6 balls went from C into A, and in the end, they all had equal amounts. So I put a 1, 2, and 3 just so I could kind of start making the data make sense to me. And this is a kind of problem that is very simple if you start from the back. We know there are 45 ping pong balls, so in the end, I must have had 15 ping pong balls in each one. This is at step 4. Now, at step 3, to get to step 4, I'm not going to number that, it's going to be confusing. To get to that point, I had to take 6 out of C and put them into A. So let's take those 6 back out and put them back into C. That means that box A is only going to have 9. Box C is going to have 21, and box B didn't change. And I took care of those 6. They went back where they were to begin with. Then I need to take 3. If I took 3 out of B and put them into C, I want to put them back. Let's put 3 back over there. Box A doesn't change. Box B now has 18, and box C has 18 when I take those 3 out of it. And I've taken care of that step. Finally, we took 7 out of A and put them into B, so I'm going to put them back out of B, back into A. I've been putting a minus. I don't know if maybe I shouldn't put any sign there. It doesn't really matter. The point is that 6 are being moved in that direction. So when I put 7 over there, then I have 16 in box A, and I have 11 in box B, and I still have 18 in box C. Notice that nothing changed in box C. Now, when you make your answer, go ahead and write it out neatly so somebody can see it. A has 16 balls. Box B has 11 balls. And box C has 18 balls. This is in the beginning, before you moved it around. When you start from the end, you take the information, you kind of organize it so you can work with it, realize you've got 4 steps going on, and in the 4th step you have equal amounts. That's your starting place, and go backwards. Number 15. Clarice is 9 years old, and her sister is 21 years old. How many years ago was Clarice's sister 3 times her age? So at some point in their past, their ages looked like this. Clarice's sister was 3 times her age. The hint, of course, we've used this hint before, the difference between two person's age is always the same. Again, we've talked about this before. I use the word static. What doesn't change? The thing that doesn't change is that their ages are 12 years apart. And so whatever age they were at the time, pretend like that matches up nicely, the sister is 12 years older than Clarice. That makes it pretty clear that each box must be 6. So when Clarice was 6, her sister was 3 times her age. If Clarice is now 9 and it happened when she was 6, always make sure you answer the question, how many years ago was the sister 3 times her age? The answer is 3 years ago is when that happened. Because now Clarice is 9, it happened when she was 6, so that's a 3-year difference. I'm going to continue working the challenging problems on this recording. Remember, challenging problems usually means they're just a different type. They're not always hard. Sometimes they're hard in funny ways. Number 1 says that Roxanne and May share a sum of money equally. Roxanne's share is a multiple of 8, and May's share is a multiple of 12. The key here, this is Roxanne's share, this is May's share. The key is that they're equal. And so if Roxanne's share is a multiple of 8, and if May's share is a multiple of 12, then the number we're looking at, each of them must both be a multiple of 8 and a multiple of 12. Because what describes one number describes the other. They're the same number. So the question we're asking is, what number is both a multiple of 8 and of 12? In math, we call that the least common multiple of 8 and 12. When I find least common multiples, I think of 8 and 12 as prime factors. 8 is 2 times 2 times 2. 12 is 2 times 2 times 3. The smallest thing, or the least common multiple, means it's going to be larger than 8 and larger than 12. And the greatest common factor is confusing with least common multiple sometimes, right? The greatest common factor is 4 because they both have at least 2 2's. Okay, that's greatest common factor. That's how we get 4 for the greatest common factor. But the multiple is a number bigger than both. So the least common multiple has to have 3 2's in it. It also has to have a 3 in it. Notice that 2 times 2 times 3 is represented in here. And notice that 2 times 2 times 2 is represented in here. So the result of this multiplication is going to include the number 8, and it's going to include the number 12. This number that is the least common multiple is 24. So that's a number, that's the first number you can come to that is both a multiple of 8 and a multiple of 12. But here's our next question. What's the largest possible sum of money shared by them if it does not exceed $200? Again, you just have to keep all the information straight. The number shared by them cannot exceed 200. So each of these has to be less than or equal to 100 because they share it equally. So 24 would be a great answer. They could each have 24. In total, they'd have $48, and it would meet all the criteria. But that's not the most they could have. They could both have $48. And that would meet the criteria. But that's not the most they could have. So what we want to know is, if the highest number possible is 100, and it has to be a multiple of 24, how much is that going to be? Probably it's easy to estimate because there are 4 quarters in a dollar. 4 times 24 is equal to 96. So if Rosemary has 96, Roxanne, it's an R name, and May has 96, then altogether they have $192, which is pretty close to $200, and Roxanne's number is a multiple of 8. This is 8 times 12. May's number is a multiple of 12. This is 12 times 8. Look at there. And so $192 is the total. What is the question? What is the largest possible sum of money shared by them if it does not exceed $200? Thinking, thinking, thinking. Number 2, Bill's age this year is a multiple of 5. Next year, it's a multiple of 7. We just want to know how old Bill will be next year. If Bill is 20 this year, then he turns 21 next year, and that's a reasonable answer. Now, we could continue on, and eventually there would be another one that would work. My guess is, I haven't worked this one out actually. Let me pause the recording and I'll do that. It happens again, but it's not until you get to 125 and 126 before you get to another number. No, I'm sorry, I missed one. It would happen at 90 and 91. The point of this, however, I may have missed another one. Let me see. Hang on a second. Okay, there was another one I missed. There are multiple options for this. Bill could be 20, turning 21. Of course, the question is, how old will he be next year? So the answer could be 21. That's reasonable. 55. Make that point to here. 55 and 56 would work. So he could be 56 next year. The next time we have an option is all the way to 90 and 91. Sort of that's unrealistic, although people do live to 90, 91, so that would be okay to put that. 125 and 126 is really out of range. We wouldn't consider that a possible age for Bill for the next year. So as soon as you find one, you can stop. If your child is having fun and wants to keep going and find some more, they can find some more. 21, 56, and 91 would all have to be considered potential answers. Notice it doesn't say what's the youngest he could possibly be or what's the oldest he could possibly be. It just says, how old will he be? And so the fact that there's a couple of answers isn't a shock, because numbers generally work in patterns, and helping your child see when is there one answer to a problem and when is there a pattern going on that you'll have more than one answer. What I hadn't thought of when I first worked it was the fact that anytime I'm looking for one, it's obvious, but a 1 or a 6 on the end of it is always going to infer that the year before that it was either at a 5 or a 10. So as I was writing those out, I could have just been thinking about the factors of 7 that have a ones digit of a 1 or have a ones digit of a 6. As you're doing it, you begin to see the patterns and the smart ways to do it, and that's why we play with them. We play with the numbers a little bit so we can come up with good ways to solve it. Number 3, last one. Not a simple one. Just, again, mostly it's organization. There's a total of 40 round-shaped and heart-shaped gift boxes. I can draw a heart. A lot of things I can't draw, but I can draw a heart. There's 40 of these. I don't know how many of each there are, but there's 40 total round and heart shapes. Shop assistant puts 4 cookies into each gift box, but she soon realized that she did not have enough cookies to put into all the gift boxes. So she put 4 cookies into the round gift boxes, and she only put 3 cookies into the heart-shaped gift boxes. So she must have started with the round one, then realized she's going to run out, and just put 3 in each of the heart ones. The important thing is that all of the round ones have 4, all of the heart ones have 3. And then we have this interesting fact. The total number of cookies in the round-shaped gift boxes was double the total number of cookies in the heart-shaped gift boxes. And we want to find what was the total number of cookies. Now, the back of the book actually has quite a few charts that it drew. When I was working it, I saw it a little bit differently. And if this makes sense to you, then it's a lovely way to do it. I know that if I just have one set of cookies of the heart and the circle, the round boxes, then I either have 4, 8, 12. My number of cookies in my round box is a multiple of 4. The number of cookies in the heart box is a multiple of 3. We're trying to find when the round box has double the number of cookies as the heart box. So double 3 is 6. There's not a 6. Double 6 is 12. So that would work if I have 3 circle boxes, round boxes. Let me do it this way. I have a set of 3 round cookie boxes and 2 heart cookie boxes. I said I could draw hearts, and that was pretty pathetic. But when I do that, it meets my criteria because I have 12 cookies in the round boxes and I have 6 cookies in the heart boxes. I'm going to call this one set. And I have a total of 5 boxes, 5 cookie boxes altogether. Notice that I'm told that I have 40 total boxes. That means I must have 8 sets, because 8 times 5 is 40 boxes. We're kind of delving into ratios a little bit here. I know that I have to have 3 round boxes for every 2 heart boxes in order to have the right ratio of cookies. Double the number of cookies in round as I have in the heart. That makes 5 boxes in a set, and I must have 8 sets in order to have the total of 40 boxes. The question is, what is the total number of cookies? All right, every set, I have 12 cookies in my round boxes. I have 6 cookies in my heart boxes. Every set, I have 18 cookies. If I have 18 cookies and 8 sets, that is 80 and 64, or 144 cookies. The thing I like about Singapore math, one of the things I like is the math involved in doing this was simply counting by 4s and counting by 3s. I didn't even have to go very far. And then I did 8 times 5 is 40. I did 18 times 8 is 144. The amount of math that I had to do was minimal. Look how much thinking I had to do. Now you might need to pause this and go back and play it again and think through it. And if you don't like this way, the back of the book has they just drew a lot of boxes. They had a lot of charts. If you can think through this, if this makes sense, this is a little bit of a prettier way to do it. Takes a little less time, a little less boxes, and it's very logical. Not simple, but it's not the math that we're working on, it's the thinking skills and organizing the data to help you figure out what it is. And that's the end of this recording.